Hello, welcome to Smaart Operator Fundamentals Online Session 9. If you're joining us for the first time, welcome. If you're joining us again, welcome back. So today we're going to be talking about some specialized topics, specifically in transfer function, spatial averaging, and data smoothing. You've got me today, Chris Tangeris, and Michael on the what would you call it, moderator feed? I don't know, but you got Michael here too. So today we're going to cover some information about spatial averaging. Spatial averaging being taking an average of multiple positions. And I know Jamie already went over some of this stuff in a previous session. We're just going to take a little bit of a deeper look into some of these topics, as well as the types of data averaging that we have, and then we'll investigate our smoothing algorithms as well. And so now, when we talk about system engineering, system alignment, we're using Smaart as a tool. We're the people that are making the decisions on the data. We're deciding what data we want to get, how we want to get it, where we're getting it from. But we're using Smaart, right? So we're using this analyzer, and it's a really powerful tool. There's some really fantastic mechanisms going on in Smaart. Now, it's up to you to take advantage of them. You know, if you give me a hammer, I can't necessarily build a house with it. My father probably could, but but you know, it's just in knowing how to use that tool and take advantage of everything that you have. So some of the things that we're going to look at today are really in the line of more better understanding the tool and sort of the fundamental mechanism that some of these things do. Now, one of the things that's sort of interesting about system measurement, system alignment, you know, us as operators out there, we take a microphone and we put the microphone in a space, and you know, we try to come up with a way that we can measure a response of a system with a single probe in space, you know, or many probes in space, and especially when we're indoors, we're dealing with all these different reflections, reverberance. If you have the microphone on a stand, you're dealing with the ground bounce. All this stuff causes ripple in your response. All this stuff makes the squiggly line more difficult to look at. What I want to talk about in this presentation today is ways that we can get a more clear view of the response of a system using the tools that we have available to us. Now, one of the things that, you know, sort of the way that I even talk about what we do is, you know, we take a loudspeaker system that we hopefully like the response of, and we take that loudspeaker system, we put it in an environment that may be hostile towards producing good sound. And so is it possible to take measurements that allow us to see how that loudspeaker is interacting with the environment that we're in? Can we take measurements where we can find, you know, positions or maybe a position that represents the response of our system? You know, we're not listening to concerts, you know, in the near field of our system. Not everyone is in a studio monitor type position for a live sound event. You know, we're covering really large spaces in a lot of cases. And, you know, we don't have the time necessarily to measure every single seat in the venue. That'd be awesome if we could, you know, and really get down and dirty and you know, see what every response of every area is. But practically speaking, you know, if we only have 15, 20, 30 minutes, 5 minutes to tune a PA system, you know, we have to make decisions that are going to allow us to really see the overall trend of our system with maybe, you know, a minimal amount of data. And so how can we get to that data quickly, and how can we make sure that data is actionable so that we can have data that represents the response of our system? And you know, I'm talking about sort of acquiring this data, you know, whether you like the response of the system and the sort of subjective nature of the stuff. Now, that's not what we're here to talk about today. You know, so the sound of the system, you know, it is what it is, and maybe you want to change that to be something else. That's not what I'm here to talk about with you. I want to talk about just identifying that response. So if you have a microphone on a stand, you know, you have all this different energy arrival into that microphone capsule, besides the direct arrival. If we can take multiple positions, you know, so whether you have one microphone and you move it around or many and you set them up and take many measurements at once and then average them together, we can effectively randomize out the effect of the positional anomalies when we average them spatially. And that's what we're after here. When I talk about spatial averaging, I'm talking about being able to average out the positional anomalies that you would get from location to location. So why are we using multiple microphones? Well, because it's really convenient. If you have 3 measurement microphones and you can go and set them up in the coverage area of your system or wherever you're trying to find the response of your system, that's great. You can set the microphones up and then go work on your system without having to walk back and forth and move one microphone around. Of course, especially after this quarantine, if you need the exercise, then maybe consider spending a year with one microphone before you take out more than a few. I digress. But it's just really convenient to have multiple microphones set up. And 3 is fairly typical. You don't want to have less than 3 because in order to get a spatial average, you really need at least 3, because whatever's an outlier is going to get averaged out. You can increase, you can go to more, you can go 4, 5, 6. But if you think of essentially the law of diminished returns, and we'll look at this with some data, but the difference between 3 to 4 microphones is minimal. You'd really have to go to 6 microphones, and the difference between 6 and 7 is you won't really see it. If you want to see an appreciable difference, you'd have to go to 12. In all practicality, we'll look at some data, and 3 is the minimum that you need. Right, and again, why are we doing spatial averaging? Well, we want to be able to see what is consistent in our listening area and make decisions based on that, and not sort of put ourselves into a narrow vision here of just one location. So we want to make decisions that work for an entire venue space, not necessarily just one position. And of course, there are times when it does make sense to do more of a studio, tweaky tune for one position. But in terms of venue tuning, finding the response of a venue, we're dealing with large spaces. Now I'm talking about averaging. I'm talking specifically about spatial averaging. It's important that we make the distinction that there's temporal averaging and spatial averaging. Temporal averaging is the actual fundamental FFT, what's going on with the individual engine, and how we're averaging that engine over time to stabilize the measurement. Right, so I'll jump to Smaart just so we can take a look at some of the different averaging settings. And here's just my input check to make sure everything's coming in. I'll go to my mic 1 TF, and interestingly, last week we had some discussion on why I use tabs, and today I'm really taking advantage of the tabs of this interface. I've got different examples set up on each tab, and it's a really handy way of operating this interface for me. So here's mic 1 versus the console output or the mixer output, and here's the temporal averaging settings up here in the transfer function control bar. So if we take this and we set it to no averaging, it's basically the instantaneous, not instantaneous responses, but it's a line that's showing us whatever's coming into the analyzer. Here you'll see it's very unstable. It's just a mess of data. There's no coherence response. Coherence is a statistical measurement, and there's nothing to average here to give us the statistical data. Now, if I set this just to 2 FIFO, so the next least amount of averaging, now we have a coherence response because there's some data in the buffer that we can start to average together and see how the signal to noise ratio is changing frame to frame of the measurement. The more averaging I add, you'll notice that the response seems to slow down a bit. Let me turn down the noise just a little bit so I can talk. So here's 8 FIFO. 8 FIFO is a great amount of temporal averaging for electronic measurements, where there's no noise, and so we don't need to reject any noise, but we want to see the effect of a change in our system. Maybe if we're measuring the equalizer, we'll see the effect of that change very quickly. Down to 16 FIFO. Now we're starting to get some stability. Now this can be useful if you want to see the response of an equalizer that you set. So let me just lost our measurement here. There it goes. All right, so if I were to put a filter in the system, yeah, we can see that change pretty quickly. But the measurement is just not stable. You can see the impact that my voice puts on this measurement. It's moving a lot. Look at the low frequency. There's just no stability in the low frequency. As soon as we go to the integer averaging, so 1 second, now the measurement really starts to stabilize. My voice doesn't impact it as much, and I'll go up to about 7 seconds, and I'm going to refresh the average buffer with the V key, V for Victor, and then I'll start talking and see what happens to the trace here. Right, so we've got a pretty full buffer, and you see my voice just doesn't do much to the measurement. The measurement is incredibly stable. That's what we're after. We're after that stability, and that temporal averaging. This averaging here is what lends to that stability of the measurement. If you go to infinite, it's an infinite average. Fast and slow correspond to the dB SPL values for fast and slow. For transfer function measurements, acoustic measurements, the 1 to 10 seconds is really where you want to be. I usually, 1 second's the default, so 1 to 3 seconds for a reasonably tame environment. But as soon as you have any amount of wind or different random noise things, I mean, you're 3 seconds plus is really where you want to be. So that's a bit about temporal averaging. Now, when we talk about spatial averaging, again, we're not looking at one transfer function engine, one measurement. We're looking at many averaged over a space or area in a space. So let's go PowerPoint. And so they're analogous, right? So in both senses, we're trying to stabilize our measurement and find consistency in our measurement. But temporal averaging is done to the FFT as it's being calculated. It's rejecting noise to increase the signal to noise ratio. Spatial averaging is done either in real time or with stored data, but it's done to average data over a location and find what is consistent of that space. So when we talk about averaging positions, placement for these things, again, how many positions do we actually need? What is the area of space that we need to cover? And this is one of those things where it's sort of a a bit of a common sense thing. If you want to know the response of your loudspeaker system in its coverage area, don't put positions outside of the loudspeaker's coverage area. Unless you want to know what is the response of my system outside of the coverage area, then you see what I'm saying. It's sort of ask yourself the question. What is the question you're trying to answer, and then place the microphones in the location that's going to give you an answer for that question. So we had a few years back, we went over to Foxwoods Casino and took one of our loudspeakers and hung it up in the air, and we wanted to find out the answer to this question: how wide and how many? This is the grid sessions. So we have, to the right of this photo, there's a loudspeaker hung up on the lift, and then we taped out a grid location across the stage here. This is the Grand Theater at Foxwoods Casino here in Connecticut. And we ended up taking thousands of measurements that day. I mean, it's a tremendous amount of data that we generated. We took a microphone and we basically put it at every single location on a meter, every square meter for the grid of the stage in the coverage area of the system, and then we started looking at that data and saying, well, can we find a position that corresponds to the response of this loudspeaker system, right? So can we find how many positions do we need to average to get a good consensus view of what this loudspeaker is doing in its space? So let's take a look. Let's take a look at this data in Smaart. Right. We'll turn this engine off. So here's the Foxwoods data, and so here's the grid measured as a multi-time window measurement of the polar averaging. So here's the near field reference, same. And so if this is the near field response of our system, how does the response vary as we get into the venue, or in this case, onto the stage? Now, let's see. How many positions do we need to average together to get a response that shows us the general sort of consensus of what this speaker is doing? Well, let's start with 3. So here's 1, 2, and 3. Okay, so 3 positions randomly selected by me. Each one has a different. Actually, they're actually pretty close. Let's see. Let's do something down here. There we go. So 3 different positions. Now I'm going to average these measurements together. Static average. So multi-select the 3 measurements. Right-click, average, and we'll call this Foxwoods static av 1, and I will OK. And let's see, how does this measurement compare to the near field? Where's that there, Trace? All right. So now we're starting to see, can we see the response of this speaker in this measurement? Right. So what's happening as we get into the space? And for the most part, we follow the trend of this system, and then in the high frequency, we start to have a little bit of loss up here, which makes sense. Air is a low pass filter. So that's 3 positions averaged. Let's average more data. So I'm gonna go 1, 2, 3, and we'll do this time we'll do 4. So here's 4 positions. So 1, 2, 3, and 4. Foxwoods static 4. And we'll change the color because that's really close to the near field reference color. Okay. And so let's take a look at these 3 averages we've just created. Or sorry, the 2 averages and the near field. Right? So that's the difference between 3 microphone positions and 4. Right? So looks like we were able to get this down here a little bit better, but that could have just been the positions I selected. Now, I could keep averaging more and more positions, and we're going to continue to increase our rejection of this ripple in this measurement. But really, can you see the trend of this system with this first average here? Right? And that's sort of what we're after with this, is we want to be able to take a relatively quick measurement, 3 positions, and find the trend of our system. Now, comparing that to the near field measurement, can you see how the system changed as he went into the space? And this is something that over time you get really good at looking at data and recognizing the trend of a system, especially if you're using a system that you're very comfortable with or familiar with. If you're using the same loudspeaker system, you've measured it 100 times, whatever, you get used to what it's supposed to do. And so as you take that and move it into space, the things that change, the things that are different, end up, being really clear. If you know that this loudspeaker system has this high pass down here and you get a little bit less energy, maybe that's an issue you need to face. Or maybe that, well, we're just lost a bit of high frequency, air's a low pass filter, so why that's happening. Now at this point, can you say, okay, well, can I take this this average, and can I use one position to compare that to the average? Well, let's see. Let's pick a position here, and I'll hide the near field. So here's the average and a single position. Now, looking at the top of this trace, right? So the sort of the peaks, not necessarily the dips. Can you see how this measurement, this average, and this single position correlate to each other? Again, this is one of those things. The more you look at this data, the more you get used to seeing this. And as far as we're concerned with the analyzer, this is one of the more powerful tools that we have, is the ability to average multiple positions together. So let's see. If you noticed in the average dialog, we had a couple selections there, right? So we have the default selection of dB coherence weighted for the static average. We also have the dB without coherence weighting, and we have an option for a normalized power average. So the dB average is for transfer function spatial averaging. It's not necessarily the best choice because, like I say here in the PowerPoint, the nulls in the response get as much weight into the average as the peaks. So if you look at our responses here, these nulls here, these lower areas, they would average with the same weight as the peaks in this measurement, which is probably undesirable. With coherence weighting, we take the single positions with the highest coherence, and those get more weight into the resultant average, which is a really powerful tool. Now, this whole thing comes from what's going on in your venue. Do you have cancellation caused by comb filtering? We have the ground bounce, reverberance, causing various levels of ripple. So if we take a look at that ripple, the coherence response is generally going to correspond with those areas of ripple. So let's take a look at another trace. I've lost my cursor. Where'd you go? There you are. All right. So notice how in this measurement where we have these nulls, we also have this low coherence. So we have a null, we have low coherence, a null, we have low coherence. So when I take this measurement, if I'm going to use this data and average it with other positions, I don't necessarily want to include this null with the same weight as these peaks, because as we look at other positions, move the microphone, right? Do you have the same sort of reverberant structure, the same nulls and peaks as you do in all of your positions? And no, each position is going to be different. So with spatial averaging, we want to reject these variances, but keep what's consistent. And so between these two, notice how the coherence response changes with these two positions. I'll add a third. So we have now 3 different measurements with 3 different coherence structures. Right? So we average these together. We'll take a look at that. And where's the third one? There it is. Right. So with the coherence weighting, we get to a point where the measurements with the highest coherence have the most weight in the measurement. So with power is interesting. Instead of looking at the coherence for information of what to give the more weight to, power looks at the amplitude, because again, the nulls, they're low amplitude, right? So we don't want to include them in the measurement the same way we want to do with the stuff that is higher amplitude. And so power weights the stuff that's higher amplitude more into the measurement. Now, let's take a look at some data to illustrate this. Hide this measurement, and we'll go to class data. So here's a manufactured response, right? So we've got this ripple, right? And so this was a measurement that was created basically in an Excel sheet, because you can import data as text, ASCII text into Smaart, and so this was manufactured data. And here's a second piece of manufactured data, and notice the ripple here in these traces, they're complementary, right? So for each peak, we have a deep dip, peak, dip, peak, dip. And so let's take a look at this data. Let's take a look at what happens if we go through the different types of averaging. So we have our first, which is dB. So we'll do a dB av. So we'll take off coherence weighting. Okay. So our dB average just basically cancels out the ripple, right? It's gone. They're complementary to each other, so they go away. Let's take a look at what happens with coherence weighting. Now, this is going to be sort of silly because the coherence is perfect, right? It's a manufactured measurement, so there's no coherence to weight. So we should expect the exact same thing as the dB. So dB co. Right? And so sure enough, they're the same thing. Right? But now let's take a look at what happens if instead of dB, we use power. And so again, what power is doing is we're taking basically from 225 hertz to 8.8K, normalizing our measurements, so it's a normalized power average, and then the frequencies with the higher amplitude get more weight into the average. So we'll call this a norm power. So we select power, coherence goes away, right? So we're no longer looking at the dB of coherence weighted, we're just looking at the normalized power, and that's really close to one of the other colors. So let's do this green. I feel like Bob Ross. Let's do this green here. All right. So now, looking at that power average, you'll notice that, well, now this ripple, it's not necessarily canceling out, it's adding up, right? So we have some indication of something going on there, and you'd probably hear that if that were real data, you'd probably hear it, but it's not. So let's take a look at some real data and see how these all compare. So just like a cooking show, I've already prepared some measurements here. So last week when we had the 3 microphones set up for the averaging that Jamie did, I've left the same measurement configuration, and I've added to that a dB average, a coherence average, and a normalized power average. So this is going to be real data. So mic 1, mic 2, and mic 3. All right. Okay, make sure we're all. So what's really interesting about when you're running a live average, as long as the contributor engines are running, they're contributing to that average. So I'm going to hide the active display for these measurements. And so here's, we'll start by looking at the coherence weighted. So here's the coherence weighted average. And we'll compare that to mic 1 TF. Okay. So there's the coherence weighted average and the individual measurement, or one of the individual measurement positions. So let's take a look at the dB average. Right, so the dB versus the coherence, it's not too different, but the coherence response comes up just a bit with the coherence weighted average. Again, all the frequencies with the highest level of coherence get the more weight into the resultant average. So if we look at normalized power, we don't have the benefit we do in the coherence trace. Increase the averaging here as I'm talking. So they're all sort of telling us the same story, right? One of the reasons why we like dB coherence weighted is because the rooms that we're in have, generally have a reverberance, and we want to be able to see what is consistent in that space, and again, reject what is variant. So with the coherence weighted average, we get a coherence response that shows us what's consistent about our environment. So say if we have a cancellation in our loudspeaker due to mismatched or improperly aligned loudspeaker driver. Say you have a point source speaker where the high frequency element was wired out of polarity with the low frequency because the person at the shop that replaced the driver that just blew didn't wire the new driver into that point source speaker correctly, right? So pins 1 and 2 are swapped. And so the response that you get from that system has a cancellation at the crossover between the high frequency and the low frequency driver. Well, there's a chance, depending on how that system's working, that you may or may not see that in the coherence response. We want to see a measurement where the things that are consistent in that system show up everywhere. I guess a better example would be if you have a loudspeaker that's away from a wall, and there's cancellation caused by the wraparound, the reflection of that system in that environment. Well, that cancellation is going to be everywhere in the venue. So with your coherence weighted average, you're going to see in each measurement position that there's a cancellation of that energy that's going to show up in every position. Again, we want to see reject what's variant and see what's consistent. And dB coherence average is really, really useful for that. All right, let's see where we at for time. 45 minutes. Wow. Let's see. Do we have any questions on where we are so far? I didn't realize that I had gone for 45 minutes.
Well, you actually haven't. It's only 2:30, so you're in good shape.
Okay.
But I definitely think if you want to just maybe reiterate. A lot of people are saying, well, okay, so which type of averaging should I use then? So, in what applications would we want to use these different types of averaging?
Sure. So the default settings of Smaart have been chosen over, basically the life's work of a number of people. The default setting for dB coherence weighted averaging for spatial averaging is, in our opinion, the reason why it's a default, it's going to give you sort of the best, more reliable answer when you're talking about a venue where there's reverberance, there's positional anomalies and stuff. We want to give more weight to the microphone locations with the best coherence. As far as the temporal averaging, again, for acoustic measurement between 1 and 10 seconds, the more noisy your environment, the more noise you have, say the more wind, that kind of stuff, the more averaging you may want to use. Is that hitting the mark on that, Michael?
Yeah, I think so. And I think the point to make is that hey, it's not necessarily that one of these is superior than the others. It's that they're different tools that we want to use in different applications, like you said, depending on the question that we're trying to answer. Yeah,
and it's feel free to practice, play, and see what you like. Like I said, this is a tool. So dB coherence is the default in my preferred setting. Of course, you're welcome to play, but yeah. All right. Anything else on the spatial averaging stuff?
No, I think we're in pretty good shape. So I guess we can go ahead and move on if you want.
Cool. I want to go now. We've been looking at the high resolution data, the raw sort of MTW FFT. What I want to do now is take a look at another tool that we have, and that tool is smoothing. And so with smoothing, what are we trying to do with spatial averaging, right? We're trying to find the trend of our audio system. Smoothing is something that can help you find that trend. Now, again, it's a tool. It's there to help you. With great power comes great responsibility. So how much smoothing do you actually need to use? Well, it sort of depends on how your measurement is. And are you looking at the smoothing of one location versus the smoothing of a spatial average? So let's say this. What is smoothing, right? Well, smoothing is an average of overlapping bands. So if you think back to when we talked about banding in the spectrum measurements, banding is a summation of data within a band. And so let's take a look at that in Smaart. Take a look at mic 1. So here's a 12th octave banded measurement, and I'll go back to, and this is just a refresher for those of you that started here from the beginning. So with banding, we're summing the energy within a fractional octave band. So if I go to 6th octave, 6th octave includes the fractional octave bands that are higher resolution, and that's why the energy comes up as you increase the banding size. So there's octave banding, right? So it includes all of the energy within that octave band. And so as I go down, higher resolution, you'll notice the amplitude apparently comes down as well, but the amplitude's there's not less energy in the measurement, it's just less energy per band. So smoothing is analogous to this, but it's not the same, right? Because smoothing you're not fixed to a specific band. When we talk about smoothing, we have the same values, right? We have none, 48th octave, 24th, 12th, 6th octave, 3rd, but these aren't fixed values, right? It's not fixed on a 48th octave center. They're overlapped, right? So it's the average of overlapping bands for a given width. So if you look at a single measurement, right? And then we smooth that, so there's no smoothing, 48th, 24th, 12th, 6th, 3rd octave. The trace doesn't come down in amplitude like it does with banding, because we're not changing the amount of energy in each octave band. We're just changing the width of the energy that we're averaging. So this is one of those things. It's really handy that when you press in the averaging, the up and down arrows of your computer become hotkeys for that drop down. So you can really quickly go between the smoothing options. And this is one of those things that can be really helpful when you're in situation, just to sort of check your eyes and see where you're at. Now, how much smoothing can you use? And this is where you need to be aware of what your system's doing in terms of the positional anomalies and what actually is in your system. Because if you have one position, you're making all of your decisions off of one position, then you're also making decisions based off the positional anomalies of that location. So if we take a look at, let's see, I have some data here. So here's no smoothing is the blue, 12th octave is the orange, and then octave smoothing is the red here. And you'll notice with that octave smoothing, because it's including this out of band data here and here, it ends up being a much lower amplitude than the 12th or 48th octave or unsmoothed value. So this is one of those things. You'd probably hear that peak, and it'd probably be it could be a real issue, but the octave smoothing doesn't necessarily make that obvious. So the more you smooth, sort of the less blurry the image becomes. And so going back to the spatial averaging, one of the more effective things you can do is just start off your session, find your initial response of your system based on a spatial average, use smoothing to sort of see what the overall trend of that average is, and then you can determine if you can find an individual position that will best represent that location. So let's take a look at, before we do that, let's see, I just for fun here, I set up one microphone, and then I took that microphone and made an engine for each smoothing value. So this is something we can do in Smaart, where we take the measurements detail settings, and we just say don't follow global. And so for each of these measurements, I assigned the smoothing values to be exactly what their name is. So mic 1, 12th octave smoothing, etc., etc., etc. And so let's take a look at what these give us. Okay. So that's one measurement with all of our different smoothing options. And what's interesting is down here in the low frequency, where we start to have a considerable amount of ripple, and we're inside, we're in our training room. This isn't a large open venue space, but that octave smoothing really just kind of sees right through that. So let's take a look at this, and not just one microphone. Let's go and take a look at this as many microphones. So we'll go back to our multi-mic tab. Okay, so this is going to be an average of these three positions, and this is a dB coherence weighted average. So it's a dB coherence weighted average of the three microphones. And we'll start with no smoothing. And so here's our measurement average. Okay, so you can see of each individual contributor, they each have different values of coherence. I'll hide the average just for now. Right, so I want to get a measurement that reduces all this ripple and gives me more of a consensus view of the response of the system in our area here. So I'm going to capture this. I'm going to capture this whole group here. We'll call this okay. So now here's the data we just captured. So there's the average, and here's 48th octave smoothing, 24th, 12th, 6th, and 3rd, and then octave. Right, so now here's a question. How does this compare to the near field response of the system? Well, as convenient as it is, I have a near field measurement here. So let's see, what does the average look like compared to our near field? Oh, pretty close. We can see in our average, this low frequency energy seems to be coming up. So is that consistent in our venue? Again, possibly, if it's in every microphone position. As we get here in the high frequency, things start to come down a little bit. Again, air is a low pass filter, so we've lost a little bit of high frequency just because of the distance. So let's see, if I take this average and compare it to an individual position, right, can we see the trend in that individual position? I'd say we sure can, right? So here's mic 2, mic 3. So mic 3 seems to be a bit of an outlier. The energy in mic 3 doesn't seem to match the energy of mic 1 or 2 as well. So smoothing helps us see those trends, right? When we go to no smoothing, it's just high resolution data. We're in the reverberant field of this room, and so we have ripple. Adding some smoothing helps us reduce that ripple and see a more clear view of the trend of the system. So this is with again, this is looking at the smoothing of an average and then comparing that average to a single position. So as far as we're working through a system, what's really nice to do is to be able to take your initial measurements of that system, take an average of the response of a system, identify the trend of that system, and then compare that trend to an individual measurement. And smoothing really helps you identify that trend. Now, of course, you can go too far. I mean, I love this image that Merlin Van Veen had made. It's the Mona Lisa smooths, right? So the more smoothing you use, the more blurry that image becomes. So again, it's the higher the resolution, the more the more ripple you have, the more fuzzy, I guess you can say, the measurement is. But when you take a bunch of high resolution data, average that together, you start to see the consensus of that information. Smoothing, then on top of that, helps you really nail down the trend of that system. And so, can you do all this stuff with one microphone? Yeah, of course. It's just you're just moving your microphone around to get the spatial average and then looking at the smoothing of that. Again, one of the more powerful things we can do with this tool that is Smaart is just have those live averages running. Have the ability to look at in real time those live averages. All right. How we doing, Michael?
We're doing very well.
All right.
How are you doing?
Oh man, I'm good. I feel like I drank too much coffee and I'm talking too fast, but that's how these things go. It's hard to judge when your audience is a stuffed giraffe.
Well, I think one point that you made that's really important, and I think it's probably worth reiterating, is that these controls are on the top level, so we don't have to be married to them.
Yeah,
like you said, flip through a couple of smoothing options, and that'll give you more context on the data. And as Jamie's pointing out in the chat right now, it's all about how to give yourself actionable data as quickly as possible.
Yep. Yeah, exactly. And I mean that's the name of the game. How can we get usable data as fast as possible? Because we don't necessarily want to be spending all of our time noising a system. Me personally, I want to get to listening to the system as soon as possible. Take my initial measurements, place the initial filters if I'm using them, or whatever the initial decisions are. I want to get to sit listening to the system as soon as I can, and averaging both spatially, temporal averaging to settle down the actual responsiveness of the measurement, smoothing the measurement to give yourself better idea of the trend of the system. These are all tools that are incredibly powerful, incredibly helpful towards that goal. Are there any other questions we have hanging out?
I think that pretty much covers it, man. I think we're all set.
Great. Well, this is fun. I'll see you guys next time.